This is a project that I dreamed up myself one day when I was playing pool, and my kid asked me, so how does it know that the cue ball comes out over here and the rest of them go over here? I'm like, I have no idea. So maybe it sorts them by weight, or maybe it sorts them by size, or maybe there's a magnet, So we looked into it, and as it turns out, the way that they did it wasn't nearly as cool as I thought it was going to be mathematically. So, but I thought, what a cool math problem that would be if you could have the kids make a trap door that would let heavy things pass and light things go through. Or, let light things go across the top and heavy things drop. And could you turn that into a math problem? So I was just sort of messing around with it and eventually came up with this fine piece of equipment right here, okay, which, for nothing, anybody could make a couple of ring stands. And I just pushed it and pushed it and pushed it until it turned into a math problem. And then it turned out to be pretty appropriate for teaching graphical analysis of systems of equations, systems of inequalities. And it actually just sort of turned into something. And the reality is that the cue ball is just slightly bigger. And as it rolls down the slot, there are these two metal rails that just pick the cue ball up, and the cue ball just rolls down a different ramp because it's just slightly wider, and very precise metal rails just lift it out of the trough. I thought, well, that's not all that cool. I thought it was going to be something with like magnets or who knows. So in my imagination, I thought it was this. So this is the activity, and this is a lengthy one. It takes my kids 4 hours to do this. I assume that you guys could do it in, I don't know, less than that. And although it's not algebraic whatsoever, it is strictly graphical. This is very hard. I had 10% of my kids could actually do this. And it took a week of solid instruction and thinking about it after we'd done all of this other graphing. So here's the challenge. We're going to have two balls. One of them is going to be a golf ball. One of them is going to be a lacrosse ball. Now, the golf ball and the lacrosse ball have, different sizes, and they have different weights. So what that means is this weight has to pass. So can you imagine? Here is the scenario. Here's the rubber band. Okay? Here's the setup. And I have to tape this down. It's not quite ready for prime time. But okay, that's pretty simple, right? But the idea is that some things are going to pass and some things are not. And then you can change the amount of pre-tension by adjusting this thing up or down. Okay? So now, it's quite a bit softer. And then you can change it even more. So the idea is that I'll have to tape this down. But it has to allow the golf ball to roll through, but it has to allow the lacrosse ball to drop. But the question is, how far does the rubber band have to stretch in order for the lacrosse ball to drop?
Drop all the way out?
Yep, it has to do this. It has to do this, and it has to fall out the hole, basically.
The opening has to be greater than the diameter of the ball.
Excellent. So the opening, go ahead.
But it's, actually no, where is the rubber band in relation to the end of the door, with the little trap door?
It is intentionally placed at exactly half the diameter of the ball. The little rubber band is attached at exactly half of the diameter of the ball, so that when it is falling through, it is directly there. So how much displacement is represented by the ball falling through? And you said it is the diameter of the ball. Ooh, so you have to find a mathematical relationship that will allow this rubber band to open the diameter of the ball without the force overcoming the weight of the ball. I can say that one more time. You have to find a mathematical relationship that will allow this door to open this far before it gets too tight, and it won't open any further. And so what does that mean graphically? Well, so the idea is, you guys know that Hooke's law, spring constant, the farther you pull the spring, the the more force, and it's a linear relationship, right? And so a whole bunch of rubber bands, and a whole bunch of spring scales, and a whole bunch of these little custom doohickeys, okay? And you can just take this and hook it on the edge of your table. You can put your rubber band around this, and then you can put a ruler like this, and then you can basically pull this, and then you can get a instant reading of displacement versus force. Does that make sense? And then if you can displace it this much, read the force, somebody can write it down. Displace it this much, read the force, somebody can write it down. You do it enough times and you get points, right? And then you get a line, theoretically linear. And then you do that for several rubber bands and you get several different slopes. Make sense? Best line's the best fit. And just kind of thinking this through logically, what does a steeper slope represent in this scenario? In terms of the rubber band, what does it mean?
Tighter rubber band.
Tighter rubber band. Yeah, exactly. Okay, so now the slope is related to the physical properties of the rubber bands. Okay, then to the design target. So what we're going to end up with is something that looks like this. You're going to do something that looks like this. Y equals, I'm just making this number up, y equals 40. That's the lacrosse ball. Y equals 30, I'm making these numbers up. That's the golf ball. Here's your displacement. At some point, there's going to be some sweet spot where the correct rubber band is going to cross these lines in the proper fashion to allow the golf ball to roll across, but the lacrosse ball to drop. There's no algebra involved, but it's like systems of inequalities with multiple constraints and a ton of logic and some testing and then applying it. So here's the final result. It's going to be like this. You are going to come up to me with a rubber band, and you can put a little tag on it. You're going to say, you're going to test a bunch of different rubber bands, and I suggest that you pre-stretch these, okay, because they actually change over time. And then you're going to come up with two things. One of them is going to be your choice of rubber band, and the other is going to be you're going to tell me the pre-displacement that's going to be required, and then without you ever touching or testing it, you're going to say, okay, this rubber band pre-stretched this many centimeters will allow the golf ball to roll and the lacrosse ball to drop, and I do it and nobody touches it but me, and then we just see if it works. And I can tell you that, like, this is engineering right here. You know, their kids are like, what? I can't test it? Well, I can say you can come up here and mess around with it, right? But you can't try it out. There's no trial and error. Like if you go to design a bridge, you don't just like build it and then like cross your fingers when the first truck rolls across, you know. It has to be right, and you have to use your math model to know that it's right. So what do you need? Well, first of all, you're going to need to come up here and just sort of explore what we have. I have a variety of rubber bands. Some of them have letter markers. Some of them have gotten lost. I have the two balls, which you can measure whatever measurements you think might be important to know about. And then I have a bunch of these spring scales, which some of them will be useful, some of them will not. You'll have to figure it out. Some of them are so stiff that it's ridiculous. Some of them are super stretchy, and they're not very useful. So you'll have to figure out which of these will actually be the best tool. Then I have a bunch of these guys so that you can pull against. And so anyway, we have the y-axis and there's the x-axis, right? And then there's the two lines that represent the weight of the different balls, and then the other two lines that form a box, correct? So, and it's that box that's the sweet spot for our design target. What does this box represent, and what? We know that this is the weight of the lacrosse ball and this is the weight of the golf ball. But what does this line represent? Can anybody describe that verbally? What does that?
Minimum threshold.
That's the minimum threshold for the trapdoor opening, and this is a minimum threshold of.
Please, that's open for it.
Okay, Excellent. And as far as the golf ball is concerned, we want that to be 0, right? Okay. So what about this line then? What does this represent?
How far the rubber band needs to stretch in comparison to the previous number in order to let the cross ball through.
Right. So this is the additional displacement. And so what was the line when you guys ended up doing this, when you picked a rubber band, how did the rubber band have to cross our target area in order to be a successful candidate for our project? What lines did it need to cross? And the reason I'm asking you guys this is because, I mean, did you consider this to be a fairly challenging conceptual problem? Yeah, like my kids were just stunned, right? They're like, whoa! You know, I really had to work them through this, but in the end, I thought it was great because they really had to understand that certain points in the graph had a lot of meaning and certain points really didn't mean much. So, because when we graph things like, you know, the quadratic equation and you solve it, well, what are you doing? You're just like seeing where it crosses some line because maybe that would have some significance for somebody somewhere, right? But what, you know, is that significance? And so the idea is to try to teach graphing visually, graphically, and understand the significance of some intersections before we try to like solve systems of equations, to just try to get it conceptually. So, like, let's just take this rubber band right here. What does this point represent? Good. So the idea is that the golf ball here will stretch the gate open that far. So what do you think about this candidate then? Not going to work, right? So where does it have to cross? It's got to be this guy, right? Because then here, this golf ball will not open the door at all. And then what about up here? What's this? At this weight, what will be the displacement of the... Yeah, because it should open this distance, correct? Right. And so, like I said, we probably spent 2 weeks on this project, about 4 days actually doing it, and about another full week just like doing graph after graph after graph, interpretation after interpretation, so they could actually look at this and have some concept of what it meant. Because, I mean, we have done it so much, we don't really appreciate how bizarrely abstract these lines are. Yeah. So, are we ready to test? All right, so who's ready? You got a table that's ready? So you're going to come up with your rubber band, your pre-displacement, and you're feeling confident. Well, let me show you how I do this, and then you tell me what number it should be. All right. I'm going to call this where it basically goes slack 0.
Right.
You want that?
That's what that was for us 8 yesterday, or 0.
Yeah, can I just measure that?
So you want 13 total.
Total.
Okay, so you want 3 more in addition to that. We could do it right here. Okay, so it's going to go up to like that.
Yeah.
Same as the other group?
All right.
And you're doing the same.
Oh, look at that.
So far, okay.
All right.
It's either slightly smaller or slightly larger.
Oh, look at that. Okay, success. See if we got it here.
Okay. Here we go. Let's try it. I'll call first.
Oh.
That did not work.
No, it didn't. That sure ain't gonna work. Okay. Excellent try, though. Okay.
I'm not gonna have an that. We're gonna go right by.
It's just gonna roll right on through. Okay, halfway there.
And this should open about 2 inches.
Oh.
About 2 inches. Yeah. Look at that.
Oh.
Nope.
We supported each other.
Things.
Go, baby, go, go, go.
Oh, that looks good.
Lacrosse balls. Go down.
You did well, guys. Awesome job.
Go down.
Oops. Do that little nudge there.
Go down. Go down.
Look at that. So I have this like personal goal in my math class that at least once every couple weeks, I want to have some student like high five me because they got the right answer. Because, like I was saying, it's that emotional component of learning. Like when you have a bunch of people going, yeah, you know, like you have affected them in a way different than like turning in a piece of paper or whatever. Like your typical math class looks, you know, like here's the book, here's a quiz, you know, and people get excited about things and little challenges, and so I just feel like even if they don't learn a lot of math, I feel like the powerful logic in here and the fact that they're excited about getting something correct is great. You know, even that is an accomplishment. I'm not making this stuff up. Our kids can really do this stuff if you work them. So, but it is hard. How realistic is it to do this, honestly, with a class where you have groups, right? And then, but you need an individual assessment. Every project gets basically a paper mock-up version afterwards, and I can collect it and grade it right in the grade book.